Okay, good afternoon, everyone. So the lectures today will continue about symmetric and positive definite matrices. So remember last time we say that a matrix is positive definite if you have this quantity X transpose AX is positive for every non-zero vector X, okay, except when X is a zero vector. And we gave an example, but the example when I did last time, it was not correct, okay, so I correct it here again. So, so remember we consider this matrix sorry I need to fix up my camera. But anyway, so remember we consider the matrix 1, 1, 1, 1. All of them are ones, yeah. And what we so let me stop sharing. I pause the recording a bit, yeah. Okay, so we have a matrix 1, 1, 1, 1. Okay, and when we want to check whether this matrix is positive definite or not. So we take a vector x, x1, x2 in R2, right? And then if we take the X transpose AX, then it will be X1, X2, 1, 1, 1, 1, right? And X1, X2, yeah? And remember last time we compute this one, it will be X1 plus X2 square, okay? Now, if you put X1 equal minus X2 equals some alpha, or alpha could be non-zero, okay, could be non-zero, then X transpose AX equals 0. So the matrix not positively definite. So the matrix for non-zero X. So the matrix A is not positively definite. Okay, so A is not positive definite. Yeah. So last time we made a mistake. I made a mistake that I claimed that this one is positive for every X, but nobody corrected me. Okay. So anyway, so now we go back to the slide and so now if we go back to the slide, yeah. So the matrix positive definite when you have this definition, this quantitative is positive for every non-zero vector X. And only when you have a zero vector X, then it is 0. So this is another example. So in this case, you see, I mean, it's a sum of 4 squares. And the only ways when all of this 1 equal 0 is you have x1 equals 0, x3 equals 0. And hence x2 has to be equal 0. So the only way it equals 0 is when it's a zero vector. And then in order to check whether the matrix is positive definite, you can check the principal matrix of order k from 1 to n. And then you check the determinant. Okay. So for example, in the previous matrix, the first principal is just the number 2 in the top left corner. The second principal matrix suborder 2 is just a 2 by 2 matrix, start from the top left corner. And the principal matrix suborder 3 is the full matrix. And it's a bit lengthy to check the determinant of each component, right? I mean, if it is a single number, then it's easy to check. It's a determinant, it's just that number. But if it's a 2 by 2 matrix, you have to take 2 multiplied by 2 and then minus 1. So it becomes 3, so it's positive. And for determinant of 3 by 3 matrix, there's a lengthy formula, or you have to do Gaussian elimination and you multiply the diagonal entries. So it's a bit lengthy. So now another way is you just check the eigenvalues. So you check the eigenvalues, then if all the eigenvalues are positive, then the matrix positive definite. Okay, so now why do we study this positive definite matrix? Well, because if the matrix is symmetric and positive definite, then it has a Cholesky factorization. So remember before we have a LU factorization, right? So the product of L times U, okay? Two separate matrices, but now you have only one matrix R, and A equal R transpose R, yeah? So what is R? So R is an upper triangular matrix, okay? So then what is R transpose? It could be a lower triangular, right? So it's a lower triangular. So this is a special case of the LU factorization when the matrix L and the matrix U are related, right? And you will see that, you know, I mean, it will be twice faster for the Cholesky factorization compared with the LU factorization. So now I want to prove this theorem at least one way, yeah? So I want to prove that if the matrix has a Cholesky factorization, then it's symmetric and positive definite. Okay, so I prove only one way, so the other way is a bit tricky. So let me share my camera again. So now we say that A is R transpose R, yeah, and R is upper triangular triangular, yeah, and on the elements of on the positive, sorry, on the diagonal entries of R are positive. Okay. Then the conclusion is A is symmetric and positive definite. So can you see that? Positive definite, yeah. So you see, this is if and only if, okay, if and only if. So if it's symmetric positive definite, then you have this condition. And if you have this Cholesky factorization, then it's symmetric positive definite. But now I prove only one way, so I prove only one way. So the other way is not easy. So you can read it in the lecture notes, okay? So now I claim that if you have those three conditions, then the matrix symmetric. Okay, so now I claim that it's symmetric. So A is symmetric is when A transpose equal A, right? So now A transpose is R transpose R, the whole thing transpose. Then, you know, I mean, this one you can rewrite it. the transpose of the product become product, you know, of a transpose but in the reverse order. So remember you have AB transpose, it just B transpose A transpose. So this one is from linear algebra, yeah. Okay. And now when you transpose the matrix twice, it returns to this original position. So therefore, this one is just R transpose R. Yeah. And so now this one is just equal the original matrix A again. So by definition, the matrix asymmetric. Okay, so asymmetric. So asymmetric. Okay. So RJJ is diagonal entries. Yes. So RJJ is just a diagonal entry. So this one is just diagonal entries. Yeah. So J from 1 to n. Yeah. So any more questions? Real doesn't make sense. Yeah. On the slide, if you go back to the slides, very good observation. Now, if you go back to the slide, well, the slide, no, the slide said that RII is positive. Okay, but Rij equals 0 for I bigger than J. So it just means that it's an upper triangular. Okay, so upper triangular, but the diagonal are positive. Okay, that's okay, it's okay. I mean, it's a tiny detail, but it's very important. Okay, so it will be important when you see the proof, yeah? So, but very, very good observation. At least you are not sleepy, okay? So, yeah. So now we prove that it's symmetric already. So now we need to prove that positive definite. So in order to prove it's positive definite, now you have to prove X transpose AX is positive for non-zero X, yeah? So now it's become tricky. So now you have to write down the matrix A as R transpose RX. Okay, so this one is a vector X, yeah? And this one, so remember the formula up here. So this one is just Rx, the whole thing transpose. Okay, this two term, yeah? Time Rx again. Okay. And if you remember, so now you can label this one as Y transpose Y. Okay, so let Y equal Rx with Y equal Rx, yeah? And if you remember Y transpose Y, what is that? So Y transpose is Y1 up to Yn like this, yeah? And then Y1 up to Yn. Okay, so when you sum up, so it become Y1 square, Y2 square up to Yn square. Okay, so this one definitely greater or equal 0 for all value of Y, on value of Y, on vector Y, yeah? So now, but what I want is strictly greater than 0 for non-zero Y. Okay, so that I want one more step. Okay, so what happened if Y equal Rx equals 0? So if Y equal Rx equals 0, then My claim is that x has to be equal to 0 because what? So if Rx equals 0, okay, it means that y equals 0, then my claim is the vector x has to be equal to 0. Why is that? Well, somebody observed the matrix has a special structure. It's upper triangular, right? And all the diagonals are positive. Yeah. So remember, remember you have the matrix R look like this. The matrix R look like this. So R11, then R12, yeah, R13, for example. So suppose n equals 3. Then you have R22, R23, R33 here, yeah? Remember R is upper triangular, right? Yeah? And everything here equals 0. Yeah? And now suppose you have a vector x, so suppose you have a vector x1, x2, x3 equals 0. Well, 0 here means that it's a 0 vector. Okay? Then you see that the vector x has to be equal to 0 because you use back substitution, right? So you have x3 equals 0 because R33 is positive. Remember, if R33 is 0, then it's a big problem. Yeah? But here every non-diagonal, I mean every diagonal entries are positive. So x2 equals 0. And so on. Yeah? So you see it? So you can say that because the matrix R, because the determinant of R is non-zero, okay? Or because the determinant of R is non-zero. So, the matrix non-singular. So therefore, the only way Rx equals 0 is X has to be equal to 0. Okay? So this one is just example when n equals 3. Yeah, so this one just example when n equals 3. But you see now what you have done. So you have shown that the only way for X transpose AX, the only way for X transpose AX equals 0 is only when the vector X equals 0. Otherwise, then it has to be positive. Okay, so therefore the matrix positive definite. Okay, so the conclusion is, a positive definite by the definition. Okay, so that is the conclusion. So when it has a Cholesky factorization, then the matrix positive definite and symmetric and positive definite, and this is how we prove it. So the proof is like this. Okay, so any questions? So now for the other way, you have to read the lecture notes because it's a bit lengthy. Yeah, but it can be proved, and we just skip that. So why? Well, maybe before we give the motivation now, we give an example. Suppose A is given like this, okay? Then the matrix R is like this. And somehow you can think the matrix R is like the square root of the matrix A, right? Because every positive number has a square root. So here every positive definite matrix has a Cholesky factorization. So the Cholesky factorization plays the roles of the square root of a matrix. Yeah. And here you can check that the Cholesky factorization of this matrix A is given by this. We can check by MATLAB. So in MATLAB, there's a function called CHOL, which is just an acronym for Cholesky. It will compute the Cholesky factorization for you. So let me share it with you. So now suppose I share my MATLAB. One second. So my MATLAB is still okay. So I put in my, well, I have to share my MATLAB, yeah. So I'll share my command windows here. So suppose I put in my matrix. So you can see my matrix, yeah. So this one is 2 minus 1, 0, 2 minus 1, 0, and minus 1, 2, minus 1, minus 1, 2, minus 1, and 0, minus 1, 2, 0, minus 1, 2. So you see this is a matrix, and you put in Cholesky of A. Then you got, you see this one is square root 2. This one minus 1 over root 2. Okay, so this one is exactly the one we had on the slide. Yeah. But now what happens if you enter a matrix that is not positively definite? So remember we have a matrix 1, 1 at the beginning, yeah? So this one is not positively definite. And now what happens if you type in Cholesky of B? Well, say matrix is positively definite. So somehow it's very smart. But recognize that the matrix not positively definite. Okay. And if you don't want MATLAB to print out the errors like this, then there's another way. So if you type help, CHOL, yeah, then it can give you so if you give R comma P like this, yeah, then it will give you so if A is not positive definite, then P will be a positive integers. Okay, so you can check. So now suppose I give this, oh sorry, suppose I say RP equal Cholesky of A. So you see that R is given by this upper triangular matrix and P equals 0. So the matrix positive definite. And now if I replace A by B, well, you see R equal 1 and P equal 2. So this means that the matrix not positive definite. Otherwise, it produces 2 by 2 matrix upper triangular here already and P equals 0. So you see, so there's two ways to check whether the matrix is positive definite, right? I mean, you can use eigenvalues or you can use Cholesky factorization. So now if you use eigenvalues of a matrix A, you see all of the eigenvalues are positive, and eigenvalue of B, good point. So how does it find R? So I think the algorithm is not hard, but it's a bit lengthy. So I think I will give a reference for you to read. Okay. So, but essentially, It is a combination of Gaussian elimination and finding the square root. So I cannot explain it in 1 or 2 sentences, but it could be done. Okay. Yeah. So let me try to look it up a good reference, and I post it on the lecture notes website. Yeah. Okay. But I think we have to move on. Yeah. So because we have so many topics in this course. So now, so why bother to study Cholesky factorization? Well, because if you can, then the number to compute the Cholesky factorization is only half the cost, the number of flops, yeah, half the cost of the LU factorization. So remember, LU factorization took to n cubed over 3, and this take only about n cubed over 3, yeah. And so suppose LU factorization take one day, then this one will take only half a day. Okay. And see now, suppose you try to solve the linear system Ax equal B, yeah, then you can solve, like the R transpose Y equal B first, and then after that you solve Rx equal Y. Yeah, so you solve by the trick like before, yeah. And how about stability? So stability is, so there is a theorem back in the 60s. So Wilkinson showed that when you compute the solution by Cholesky factorization, then the relative errors can be bounded by this number. So essentially, this is just a condition number of the matrix A multiplied by machine y epsilon, and draw n is something very small number, depends on the size of the matrix n as well. Okay, so we stop the linear system here, and we will move on to the next topic. So so many topics and not enough weeks, I agree. But you see, that is the whole point of undergraduate. You have to study everything. And then, postgraduate or after undergraduate, you just specialize in one topics, and you try to study in a very, very deep, so undergraduate, you try to cover as many things as possible, but not in a very deep level. Okay. So any more questions? Yeah. So I'll just give you a rough idea, okay, of the topics, and then if we have time, we can go a bit further. Yeah. So any more question about this? Yes, more or less. Yeah, this is everything you need to know about Cholesky factorization. Yeah, because we don't have time to cover other details, like yeah, but roughly that is what you need to know. And so we stop the linear system here. Yeah, so I just move on to the next topic. Is it okay? And so somebody asked me, how about the practice test? I think I will cover the practice test questions in the labs this week. So we have 3 hours of labs, so we will do it. And we have 2 face-to-face and 1 online. So the online will be recorded, and I will record the solution on the Google Docs as well. Okay. So any other questions? So I can move to the next topic. Yeah. Okay. So now the next topic will be interpolation. So did I upload the tutorial? No, tutorials. You mean week 4 is the same as week 3. Remember week 3, we have 13 questions. Yeah, that's for week 3 and week 4. And the labs has been there already. The lab is just your assignments. Week 5, I will, you see, this is week 4, yeah? So usually I give the lab and the tutorial about Friday for week 5. So this Friday I will upload the problems for week 5. Okay. So be patient a little bit, yeah. So now we go to chapter 4. So let me go to okay. So now let me share with you. Let me stop this first, yeah. Maybe just leave it here. Topic 4. Okay, so interpolation. So let me show you this program before I start the lecture. So this one is just a MATLAB program, yeah. And you see that it has a mouse, yeah. It's moving. So what it does, it just capture the, suppose I put my hand on the screen, okay? And then I try to capture the pictures of my hand. So see whether, so I click on this, well, maybe the right. Well, right now you don't see anything, right? So, but let's see. So I just move the mouse around, yeah? But I trace through my hand. Just be patient. So I have to trace through my hand, and maybe it's not a very good pictures, but at least you can see what is going on. Okay, so now you see, so it's not a very good pictures, but at least you see the idea. So I put my hand on the screen, okay? And then whenever I see suitable, then I click on the blue dot. So the blue dot, yeah, but it's not a good pictures, okay? So but anyway, so whenever I click, then it has a blue dot. You see the blue dot, you see the coordinates, okay? And then the program will just use a curve. So the curve is the red curve and fit through the data. Okay, so that process we call interpolation. So you can see that people use it a lot in making movies, especially movies that use a lot of computer graphics, you know. So they have a characters moving, yeah, and then they trace or they track the movement of the characters. And then after that, they interpolate into the computer program. And then after that, they make the movement according to the story, okay? So that process, they call it interpolation, yeah? And that is the idea of the chapter we want to study for chapter 4. So let me show you. So you see that is a fun program can be written in MATLAB. So now let me make everything more precise. So we let me share the screen. Yeah? So you see the screen, yeah? So first we will study interpolation. So the process is when you have when you have a data point and then you try to find a curve that goes through those data points. And then the second part, we will study least square approximation. You see, like when you have more data than needed, then somehow you try to find a curve that fit in the least square sense, minimize some errors. So we will discuss two topics. Okay, so the interpolation will be divided into two parts. I mean, the Lagrange method and the Newton method. And then we will study interpolation errors. Yeah. So what is the errors between the exact and the curve you try to fit? And then least square approximation, where we will study how to fit the data by a line, and then by a quadratic, or by a polynomial, or by exponential. Okay, so that is the overview of the topic. Okay, so we did this one already. So this one is, I can show you that it's just a MATLAB script. Okay, and now we make everything more precise. So remember the blue dots in the pictures, are just data points. Yeah, and you can have, say, n plus one data points. Yeah, you enumerated all the points, xj, yj. Yeah, suppose you're on the plane. And now for the seamless case, we just try to find a polynomial. Polynomials mean that it's of the form a0 plus a1x plus a2x squared and so on. Yeah, and it interpolates the data. So it means that if you take, so you remember P is the red curve. Yeah, so the red curve, something like the red curve. So if you take xj at the blue dots, yeah, then it has to equal the value yj. So the xj, P and xj has to match the yj. Yeah, so that's why it's called interpolation. And right now we don't study the derivative, so we just take a point evaluation. So for example, so take a simple example. Suppose you want to find a cubic polynomial P, okay, that go through 4 points, okay? Then how do you do that? So what is a cubic? So what is a cubic? What is a cubic? What is the form of the cubic? Yes, yeah, so the cubic is just a polynomial of degree 3, yeah? So now how do you find A, B, C, and D? I mean, you don't have to give it explicitly, but x minus 1, yes, one way to use system of linear equations, yes. So you just set, say, x equals 0, right? And you get it equal 2, right? You set x equal 1, you get it equal 0. So you got 4 equations, yeah? 4 equations, and then you have 4 unknowns, so A, B, C, and D, yeah? Then you can solve it, so it's very easy, yeah? So, but now there is another way which doesn't use linear equations, okay? And that involves, I mean, this one was proposed by Lagrange. Lagrange is a French mathematician back in the 19th century. And he said that, okay, I don't want to solve linear equations. I mean, suppose I have 10 linear equations, just too much. I mean, too many equations. I don't want to do it. And he proposed this method. And now this method names after him, okay? So let L1, so L stand for Lagrange, yeah? So L1 is defined to be like this. So you see, so remember we have X, the data point, X equal, so the previous slide, yeah? So the data point is 0, 1, 2, and 3, okay? So now you have 0, 1, 2, and 3. So the very first Lagrangian function is L1 is when you take x minus everything except the first point. Yeah, so x minus 1, x minus 2, x minus 3. And in the denominator, you have 0. So this is the first point. 0 minus 1, 0 minus 2, 0 minus 3. So you can simplify this into minus 1 over 6, the product of these three terms. But now we have to pay attention to this property. If you put x equals 0, okay, the first point, then you see this equals 0, x equals 0, x equals 0, so everything got canceled into 1. Yeah. And now if you put x equal other point, say x equal 1, or x equal 2, x equal 3, it just equals 0, right? So it equal 1 at the first data point and 0 at other points. Yeah. And you can do the same. So you can define L2, L3, L4 so that L2 equal 1. Yeah. So you see L2 equal 1 at the second data point, but 0 at other points. Yeah. And L3 equal 1 at the third data point and equal 0 at other points. Okay. So you use the same trick. Okay. You use the same trick. So how do you define L2? So how do you define L2? So anyone? So how do you define L2? So what is the product? So you see the pattern. The pattern is x minus everything. I mean minus the first. Well, x minus the second data point, right? X minus the third data point and x minus the fourth data point. Yeah, except the first one. And then in the numerators, you have the first point. Sorry, in the denominator, yes. Then you have the first point minus the second point. Yes, so this one is L2, right? Well, you have to do not forget to divide it. So L2 will be, yeah. So well, so well, on the top you have x minus 0, yeah. So you have to have 3 terms, yeah. And on the bottom you have 1 minus 0, 1 minus 2, 1 minus 3. So this is your L2, right? So the product of everything except the second point, which is 1, yeah. And then downstairs you have 1 minus everything else, yeah. So then you got L2, then L3, L4, so the same principle. And so when you plot it, you can see that L1 look like this. So L1 is the blue curve. L1 equal 1 here, yeah, and equals 0 here, equals 0 here, equals 0 here. Okay, then L2 is the green one. So the green one equals 0 here and equal 1 here at x equal 1. And then equals 0, 2 equals 0, 3. Okay. So that is the 4 function L1 up to L4. And now, okay, so this one is the solution L2 and L3 and L4. Okay. And now, once you have all the L1, L2, L3, L4, now it's very easy to compute the cubic polynomial. So you see 2 times L1, 0 times L2, minus 3L3 plus 5L4. So where does these numbers come from? The 2, the 0, the minus 3, and the 5. Where do they come from? Come from the data points, yes. So it comes from the data point. Now if you remember, come from here. So 2 here and 0 here. minus 3 here and 5. So you see now you don't have to solve a linear system. You see, so you don't have to solve any linear system. You can write out P easily. But now how do you know this is a correct polynomial? How do you know this is a correct polynomial? Yes, you plug in the point. So now suppose I put in x equals 0. Yeah. If I put in x equals 0, then this one equal 1. Yeah. L1, 0 equal 1. And you got 2. And this one L2 at 0 equals 0. L3 at 0 equals 0. L4 at 0 equals 0. You see, you plug in the points, then you can see that it satisfies the interpolation property. Okay. So you don't have to solve anything. Don't have to solve a linear system. You can solve the linear system, but it takes longer. Suppose this one you have n points, n linear system, then it will take longer, definitely longer. Okay, so this one is how you verify it. So P0, you put in L1 at 0, L2 at 0, L3 at 0, L4 at 0, and only L1 at 0 equals 1. L2 at 0 equals 0, 0, so you got it equal 2, okay? And P1 is the same. You put in L1 at 1 equals 0, so cancel. So only L2 equals 0, so it equals the data point, yeah? So then you can plot it. So the blue curve, when you plot it, it goes through the 4 data points like this. So exactly pass through the 4 data points, yeah? So when x equals 0, it equals 2, x equals 1 equals 0, yeah? So now I can show you the MATLAB, how to implement this Lagrange. How do we implement this Lagrange polynomial? So you see my editor, or maybe let me share my on screen and okay, so you can see my Lagrange function look like this. So it takes in the data. So the data is xs1 up to xsn plus 1. Okay. And then it computes the product of x minus xsk over the products of xsj minus xsk. So this one is lj. Yeah. So this product is only from j different from k. So you see, I just implement this formula. So the numerator is 1, denominator is 1 initially, and then the numerator, you just keep multiplying the product of x minus the data point at k. So the denominator is, keep multiplying xj minus xk. Okay, so very, very explicit from the formula. And now how do I run it? So I have test Lagrange. So see, so I define L1 to be this, yeah, L2 to be this, 1, 2, 3, 4. And then I plot for curves, and then I plot P. So P, remember, is the polynomial that run through the data point. So I run it. So you can see that the first pictures give me the 4 Lagrangian function, L1 up to L4. And this one gives me the polynomial P. Yeah. So you can see it. Yeah. So this one is the polynomial P. And this one is just L1 up to L4. So any question? Well, otherwise we take a break and we start again at 105. Yeah. How does it work? Which one? Why does it work? So which one? You mean the Lagrangian or you mean the method or the math? Okay, the math I show you. So maybe let me go back to the slide. Yeah, so the slide. So you see, well, the slide show that the Lagrange function is just a special function that satisfies this property. Yeah. So it equal 1 at the data point, and it's 0 otherwise. So that special property makes the interpolation possible. Okay. I mean, if you can construct a polynomial that satisfies it equal 1 at the data point and 0 at other data points, then it will satisfy this, you know, satisfy the interpolation property. Yeah. Okay, so if you don't compose with, so if you don't take a linear combination like this, then how do you guarantee the interpolation property? So you see the interpolation property is this one. You want a polynomial P, so that when you plug in the data X, then it gives you the data Y. Yeah. So if you don't take the sum of 4 Lagrangian, then you don't produce all 4 data points. Okay. So does it make sense? Okay. So we start again at 105. Okay. Okay. You've seen that. You know, like you have. I mean, the polynomials can be written in a different form, but it still satisfies the interpolation condition, right? So at least now we just look at the Lagrange interpolation. Okay, Lagrange interpolation polynomials is a polynomial of this form, so can be written in a general form like this. So Lj is a product of x minus xk, so k different from j in the numerator, and then the denominator is just a product of xj minus xk. So remember, k different from j. Yeah, and you can see that when you put xj to Lj, then it equal 1 because it cancel out. Yeah, you have xj minus xk on the top, xj minus xk on the bottom, so it just cancel out. Otherwise, if you put xi different from j, just equals 0. Yeah, because one terms disappear. So that is a general form when you have n plus 1 points. Yeah, and we in our example we study only 4 points. So n is a degree of the polynomial. So a cubic n equals 3, and you have 4 points. Yeah, and your interpolating polynomials is of this form. So yj lj. So yj is the data point at xj and multiplied by lj. So now you see, now the claim or the theorem is, if you give me x1 up to xn plus 1, all of the points are different. You know, I assume that I can order the point. So this one is strictly less than, yeah. Then there is only one polynomial with degree n or less that interpolates the data. So this one is like the uniqueness, yeah. So there is only one unique polynomial. So in the Google quiz, you see that it can be written in a different form, but when you expand it out and you reduce it into the form a0 plus a1 x1 x to the power 1 a2 x to the power 2 up to an x to the power n, then it's unique. Okay, unique in that sense. So you reduce into a unique polynomial, and you can prove that. You can prove that vigorously, and we prove it by the fundamental theorem of algebra. So this theorem you might have seen it in first year algebra. Okay, so if you have a polynomial of degree n, then there exists n complex numbers and some constant c. So then you can write down the polynomial q as a product of those linear terms. Yeah. So remember, suppose you have a quadratic, yeah, then you can write down in terms of z minus the first roots times z minus the second roots. So remember, it's a complex number, so you can handle the case that the discriminant is negative as well. Okay. So, and it's true for any polynomial of degree n. So it's a fundamental theorem of algebra. So have you seen this before? So I assume that you do, right? Otherwise, we will see this again, yeah? So now I use this to prove that so existent, you see the interpolation polynomial, at least using the Lagrange form, you see that there exists a polynomial that interpolates the data. Yeah? But now I want to show that that polynomial is unique. Yeah. So now suppose I have another polynomial q, okay, of degree n or less. Now I take p minus q, okay. I want to show that p minus q has to be a zero polynomial, okay, zero polynomial. So first, my observation is it has a degree less than or equal n, yeah. And it satisfies the interpolation condition because you assume that q interpolates the data as well. So qxj equal yj and pxj equal yj is given as well. So now p minus q equals 0 at n plus 1 point. Okay. So now that's the key part. So you have p minus q equals 0 at n plus 1 point. So then you can use a fundamental theorem of algebra to write out p minus q as a product like this. So x minus x1 up to x minus xm. So remember why we can write out up to x minus xm because it's the degree m. Yeah, a degree m less than or equal n. So remember the quadratic, you write out a product of two roots only. Yeah. So now you have a degree m, you can write out a product of m linear terms like this, x minus x1 up to x minus xm. Okay. And remember m less than or equal n. Yeah. And now, what happens if I put in xn plus 1? See? So because this one is only up to xm, only up to xn, m less than or equal n. Yeah. And if I put in xn plus 1, okay, then all those terms, xn plus 1 minus x1 up to xn minus plus 1 minus xm are non-zero, right? But by this first condition, p minus q xn plus 1 is still equal 0. Remember, you have n plus 1 points here. So therefore, the only ways for this equal 0 is the coefficient a equals 0. But if a equals 0, you replace it in here. Yeah, then p minus q is 0 for all x. That has to be the 0 polynomial. P minus q has to be the 0 polynomial. And so therefore P has to be identical to Q. So that's what we prove the polynomial is unique. Okay. So is it clear now? Yeah. So now in MATLAB, you can use a function called polyfit to compute the interpolation polynomial. But this polyfit, it doesn't use the Lagrangian, it uses, like somebody suggested before, it solves a linear system. So solve a linear system based on the x and the y, and then it gives you the polynomial. Okay. So you can try those commands in MATLAB, polyfit, x data, y data, and you give a degree 3, so the cubic. After that, you plot it. Okay. So polyfit, it uses a van der Waals matrix. So let me explain it a bit. So what is a van der Waals matrix? So we had we go back to the problem. So suppose we have P0 equal, let me try to remember the data. So the P0 is 2 and P1 is 0, P2 is minus 3, and P3 equal 5. Okay. So what I'm looking for is I'm looking for A0 plus A1. I'm looking for P like this. So P is A0 plus A1x plus A2x squared plus A3x squared. Yeah. And now P0 equal 2. So I have A0 plus A1 0 plus A2 0 square plus A3 0 cube equal 2, right? Yeah. And then you have P1 equals 0. So you have A0 plus A1 1 plus A2 1 square plus A3 1 cube equal 0, and so on. Yeah. A1 2 plus A2 2 square plus A3 2 cube equal minus 3, and P3 equal 5. So this is A0 plus A1 5 plus A2 5 square plus A3 5 cube equal 5. Okay, so you write 4 equations in terms of a linear system like this. So the first one will be 1, 1, 1, 1. And then after that, you have 1 here. Sorry, you have 0 here. Yeah? 0, 0 square, 0 cube. And 1, 1 square, 1 cube. 2, 2 square, 2 cube. 5, 5 square, 5 cube. Okay. A0, A1, A2, A3. So you have to solve this linear system. Okay. Yeah. And this matrix is called a van der Waals matrix. Well, the van der Waals matrix is when you have n terms. So here I have only 4 points, yeah. But in general, the van der Waals matrix is like this. So it will be 1, 1, 1, 1, n times, yeah. And then you have x, is, in our case, x1, yeah. x1 square, x1 n, and x2 square up to x2 n, okay. And then xn square up to xn n. So this one is the general van der Waals matrix. Okay, and you can say that n minus 1, no, why n minus 1? Because remember we have n plus 1 points, yeah? So should be, so actually x, yeah, should be n plus 1, okay, sorry. So because we have x1, x2, x3, x4, so this one should be n plus 1, yes, thank you. So n plus 1. Yeah. So the last row is xn plus 1, yeah? But the last power is x to the n. Okay, so in our case, n equal 3, you have a cubic, and you have 4 points, yeah? Okay, and then and the power is 3, just stop at power 3, yeah? But in general, you have this one is, so you have n plus 1 by n plus 1 matrix. And this one called a van der Waals matrix. So van der Waals not only proposed this matrix, but he proved that, okay, so van der Waals is a French mathematician, I think in the 17th or 18th century. He proved that this matrix is always non-singular, okay, for different xi and xj. Yeah, so just look it up, but I remember that he proved that this matrix is non-singular, yeah. And you can look up the formula. He proved the determinant for this formula as well. It's the product of xi minus xj. Yeah, and I think it's not an easy proof. So that's why people name after him. And if the points are different, then the determinant is always non-zero. Okay. So you see now, if you can prove something, then 300 years later, then people will study your name, your proof, your theorems, you know, all your children, great-children, great-great-grandchildren, you study your theorem, okay? So now that is a van der Waals matrix. So now you can try this one into MATLAB, okay? But then we don't see a lot in put in the data. So you can put in this data. I can cut and paste this one into my MATLAB and show it to you. So suppose I cut and paste. I think the last one we have to give a correct. We have to give a correct correct quotation, because the quotation when I cut and paste become a special characters. So now I have to plot. So you see that? So now this one, well, let me share you the output. See, the output is identical to the polynomial we produced, yeah? So, but it has lots of data points. So the first, second, third, fourth data points, yeah? So now we go back to the slide, yeah? So the polyfit is the MATLAB commands that compute the data, compute the polynomial that fit the data for you, given in the X data and the Y data vectors. And you have to give a degree of polynomial. So this one we give degree 3, okay? Then it gives you the coefficient of the polynomial, yeah? So now the comments is MATLAB polyfit use the van der Waals matrix. So we explained the van der Waals matrix already, yeah, to compute the coefficient of a polynomial. And then the Lagrange form, okay, never use any matrix. So if you want to prove there exists a interpolation polynomial, then Lagrange form is very, very simple to construct, yeah. But the problem with Lagrangian method is, suppose you say that I don't want that data point anymore. I want to move to a different data point. Today I measure at this spot, but tomorrow I want to measure at a different spot opposite the street. Yeah. Then you have to compute the Lagrangian polynomials again, right? Because you have to take the product again, x minus xk for all new xk, right? So then Newton will say that, okay, I can fix the problem. So I can reduce the own variables. So now we will study Newton form. So the Newton form is like this. So now you see, so the Lagrange form, every time you change xk, yeah, suppose you add on new points, then you have to compute the Lagrange polynomial. But Newton said that, suppose you add on just a few new points, then you can reduce your own calculations. So he proposed a totally different method. So now we have a look at this. So suppose you have, again, yj and xj, but now there is some extra assumption. So assume that yj is not simply, data, but it's a function of the xj. Okay, so suppose yj is sine of xj, or yj is x square, xj square plus 1, something like that. So it's some function of xj, yeah? Then now we will construct, like step by step. So now suppose Pm, okay, is the polynomial of degree m, and that it interpolates the first n plus 1 points. Okay, so suppose you have n plus 1, but now n plus 1 could be a million. And now you start with m equal 1, 2, or 3. You construct upwards, yeah? So then, so Pm is given by that. So you just take out the first m plus 1 points. Okay, so m start from 0. So pick out the first point, pick out the first 2 points, first 3 points, and so on. And then you construct Pm interpolates those first n plus 1 points. Yeah. Then, okay, so what is P0? So P0 is definitely just a constant, right? Because Pm has degree m. And when m equals 0, it's a polynomial of degree 0. Well, it's just a constant. And the constant equal f of x1. So simple, right? Okay, now what is P1? So P1, now it's become interesting. So what is P1? So P1 minus P0 has degree as most 1 and satisfy this interpolation, condition, yeah? So satisfy P1 x1 equal P0 x1, yeah? So then what is P1? So, okay, so P1 is, maybe let me draw pictures, yeah? So I think the pictures here is a bit easier to explain, yeah? So remember we have x0, right? We have x1, we have x2, up to xn plus 1, okay? So it's a bit blurry, yeah? So now what is, so P0 is just equal f of, no, we don't have x0, so we just have x1, sorry, we have x1 up to xn plus 1, yeah? So P0 just go through fx0, yeah? Okay, and P1, so now P1, so P1, so this one is x1, yeah? This one is x2. So the line, so this one is f of x1. Yeah, the first point and the second one is f of x2. Yeah. So this line that go through those two data points is P1. Yeah. So then what is P1 equal? So P1 have to go through x1 and go to x2, right? So I go through f of x1 and go through f of x2. So how do you write a line that go through 2 points? x1, fx1, and x2, fx2. So what is the equation of the line? So what is the general equation of a line that go through 2 points? Anyone? How do you write a line that go through 2 points? Yeah, okay, fx1. Yeah, so it's correct. Yeah, so it will be f of x1 plus a of, well, actually it should be a of x minus x1, yeah? Because you see, you want to go through x1, fx1. So when x equal x1, then this one disappear. It equals 0. Yeah. This is a linear, so it's a line, equation of a line. Okay, equation of a line. So what you wrote down is just a constant, yeah, because yes, a is a gradient. Yes, a is a gradient. A is a slope. So how do you find the slope? So a is the slope, yeah. The slope is just you take the difference in y divided by difference in x. Okay, so it will be f of x1 plus f of x2 minus f of x1 divided x2 minus x1, x minus x1. Yeah. And now you look at this one. So this one, the f of x1 is just p1. So this one is just p1. Sorry, p0. Let's remember p0 is here. This one p0 plus f of x2 minus f of x1 over x2 minus x1, x minus x1. Okay. The question of a line, just a question of a line. Yeah. So now go back to the slide. I mean, it's just the same idea here. So if you go back to the slide, so we say that P1 is just f of x1 plus a1 x minus x1. Yeah, so it's just a equation by line. Okay. And now what is the slope? So the slope is, well, the slope that we just show the slope already, yeah. But now what you look at this one is P1 is just f of x1 plus some slope times x minus x1. Okay. Now how about P2? So how about P2? So remember, so now what happened to P2? So I go back to my piece of paper, yeah. Okay, so now I have well, so this one I just write out P0 plus A1 x minus x1, yeah. I just write out again like this in this form, yeah. And now what happens if I have 3 points? So what is my P2? So I have x1 here, x2 here, and x3 here. Okay, so I will have 3 points. Yeah, so it will be a parabola, right? Yeah, so it will be a parabola. So this one go through f of x1, f of x2, f of x3. Okay, and now you can see that in this form, yeah, you have P1 minus P0 is just A1 x minus x1. Yeah, it just go through when you put x equals 0. Yeah, so then when you put x equal x1, then it just equals 0. Okay. And now suppose I have P2. Okay, minus P1. Yeah, then it just of the form some A2 x minus x1 x minus x2, right? Because why? Because remember P2 minus P1 at x1 has to be equal 0, right? And P2 minus P1 at x2 has to be equal 0. Okay, that's a definition, yeah. So therefore, P2 minus P1 has to be a product of x minus x1 times x minus x2 multiplied by some constant. Question. So the question is, yes, it's a parabola that go through 3 points. Yes, it's a parabola because you see, I mean, that's exactly the parabola that go through 3 points. Okay, but what I want to write is of this form, so that I have a general form for n points. Yeah. So you see, so this one is for when you have 3 points, and eventually you can repeat the arguments. Okay, so y P2 minus P1 x1 equals 0. Good point, yeah? So remember, how do we define P2? So we say that P2 has to interpolate. Okay, so now if you go back to the definition of PM, yeah? Then PM equal 2, it means that P2xj has to equal f of xj for j equal 1 to m equal 2, so m equal 2 equal, so m equal 2, then this one equal 3, so 1, 2, 3. Yeah. So then P1 of xj equal f of xj for j equal 1, 2. Yeah. So therefore, if you take these two conditions, you take the difference, then you will have this condition. Yeah. Sorry. So this one is the definition. So this is the definition of P2. Yeah. So P2 xj has to equal fj. J is 1, 2, 3. And P1 xj has to be fxj for j equal 1, 2. Okay. So therefore, you can take the difference only for j equal 1 and 2. So that's why I have this condition. So strictly speaking, the definition gives you the box, yeah? And the box gives you the red box. Okay. So does it make sense now? I mean, in the lecture slide, I wrote forward, but in here, I wrote it backward. But now, does it make sense? Yeah. Okay, so in the slide, the definition gives you this condition. And this condition gives you this formula. Yeah. Makes sense now, yeah? Okay. So we can move on, yeah? So then what is the consequence? So the whole consequence of the red box is now you can write P2. Okay, so now it's a bit tricky to write, but essentially you can see that here, yeah, P2 will equal P1 plus A2x minus x1 x minus x2, right? And remember your P1, so P1 is just f of x1 plus a1 x minus x1, and then add a2 x minus x1 x minus x2, right? I just expand everything, put them together. Okay. Yeah, does it make sense? Make sense, yeah? So any other questions? So in some sense, the the parabola go through 3 points can be written in this form, yeah? And now we worry about the form correctly, yeah? You see, so in the lecture notes, so we have P1 minus P0 equal A1 x minus x1, and then P2 is just equal f of x1 and plus a1 x minus x1 plus a2 x minus x1 times x minus x2. Okay, so in general, for n plus 1 points, then you can write out Pn is of this form. Okay, so just by the definition of Pm. Okay, and this one is a Newton form. Okay, so now we worry about the coefficient now. So now we will study how do you find the coefficient. So at least you see that this is possible to write out interpolation polynomial in this form, yeah? Okay, so it's just some form, yeah, but it's possible. Okay. So now before we start writing down what is A1 up to AN, let me give the name. Okay, so the coefficients A1 up to AN are called the divided difference with respect to the point xj. Okay, and it's denoted by F, then open square bracket, and x1 comma up to xj plus 1 close bracket. Right. So now the next part is and again you see the if you take x1 up to xj plus 1, then actually it's just a coefficient of x to the power of j. Yeah. Okay, so now how do we find out the coefficient? Okay, so now this is the tricky part. So now first for P0, you can see that the divided difference of 1 point is simple. You just take essentially the value at that point. So F open square bracket, x1 close square bracket. Sorry, it's just equal f of x1, yeah, and f of xn plus 1 to f of xn plus 1. Thank you. And so now what is A1? Okay, so we discussed before. A1 is just the slope of the line, okay, that connected two points. Okay, so that A1 is just f of x2 minus f of x1 over x2 minus x1. Yeah. Or we write like this. So this is a new notation. So divide the difference over x1 comma x2 is just this one. So f of x2 minus f of x1 over x2 minus x1. Okay, so now the tricky part is how to compute A2. So in general, you know, I mean, the index are not important. So you can replace x2 by xj plus 1 and x1 by xj. You still have the same formula. So now the tricky part is how do you compute the divided difference of 3 points? Yeah. So x1, x2, x3, or xj plus 1, xj plus 2. Okay, so now we do step by step. So now remember, okay, with the new notation, then P1 can be written like this. Yeah, so f of x1 and the divided difference coefficient of x1, x2. Remember, this is a slope the line, and then x minus x1. And P2, so like we said before, just equal P1 plus, now this is before we call it A2, but now we call it the divided difference coefficient over x1, x2, x3. So this coefficient is unknown. We don't know. We don't know how to find it, but we will find out. Okay, so that is the whole point here. So now I say that P2 can be constructed in two ways. Okay, so P2 can be constructed in two ways. First, you interpolate on x1, x2, right? And then you construct x3. Or you can construct a polynomial on x2 and x3. Then you construct P2. Okay, so maybe let me draw a picture. So this one is a bit like not easy to see from formula, but you can see from the pictures. So okay, so now you have 3 points, just 3 points. Okay, so this is my x1, x2, and x3. Okay, and this one is my 3 points. So maybe up and down like this. Yeah. So this one is fx1, fx2, and this one fx3, yeah? So one way is you construct the line. So this one is the line P1, yeah? So we call it P1 in the slide, yeah? So this one we call it P1. And then after that, you construct P2. So P2 will be something like the blue parabola, yeah? So this one is my P2, okay? But you can do the other way. Well, the color is not very clear, but I suppose I use a red color, yeah? You can construct P2 by first you construct a line go through x2, x3. So I call it Q1, okay? And after that, I will construct P2 for Q1, okay? But you see, go through 3 points, we have only a unique parabola, okay? So that's why, you know, either way, you still have P2. So now if you go back to the slide, so I write P1, okay, equal f x1 plus f x1 comma x2 x minus x1, yeah, and P2 is P1, okay, plus x1 x2 x3 x minus x1 x minus x2, right? So that is the first way, yeah. So P1 and P2. And the second way is I go from the right. So this one I go from the left, and this one I go from the right. So I have Q1 equal f of x2. So remember, now I construct Q1 on x2 and x3, yeah? So that's why I start with f of x2. And plus the divided difference over x2, x3, yeah? x2, x3, x minus x2. So you see the line of P1 and Q1 are different. But now I construct P2. So P2 is Q1, okay? And plus the divided difference over x2, x3, then x1. And then x minus x2, x minus x3. So you see the difference. So the difference is when you look at the P2, sorry, the pictures should be moved up a little bit. So you see that P2 here are the same because go through 3 points, there's a unique parabola. But here you go from the left, so you got P1 here, and you got x minus x1, x minus x2, okay? And here you go from the right, you still have P1, so sorry, you still have P2, but you have Q1 here, yeah? And then you have a product x minus x2, x minus x3, okay? Yeah, let's see the index here is 1, 2, 3, here 2, 3, 1. Actually, the index here are not important, okay? Because this is still a coefficient of x squared, because you see that P2 the same, and this is a coefficient of x squared, so they must be the same, okay? And now you just use those 4 equations, then you can derive what is the formula for this. Okay, so the formula for this can be derived from these 4 equations, and that is the next slide. So if you once you see it, then the next slide will be very clear. So next slide. So you have 4 equations, yes? So 1, 2, 3, 4. So suppose you take, yeah, so I explain this. So this coefficient of x squared, so they're the same, yeah? So now suppose you take 1 u minus 3, yeah? Then you get this equation, okay? And then if you take 2 minus 4, yeah, then you get this. And you see here, p minus q1 on the left, here, sorry, p1 minus q1, yeah. Here, p1 minus q1, yeah, on the left, so they are the same. So therefore, the right-hand side of 5 and 6 have to be the same, right? And now if we just look at the coefficient of x, the coefficient in front of x, then you have these terms and this term have to be identical. And then after that, you just equate the coefficient and then you get the formula for the divided difference over 3 points. Okay, so that is the idea. And then, you know, once you prove it, then you can prove, you replace 1, 2, 3 by j plus 1 and j plus 2. And then you have the same. So the divided difference over 3 points is the difference over divided difference over 2 points. Yeah. So 2, 3 and 1, 2 over x3 minus x1. Okay. So similarly for j plus 1, j plus 2, you got this. And you can prove, I mean, similar ways for divided difference for 4 points and for k plus 1 points, you know, by induction. Okay, so that is how you compute the divided difference coefficients. So I think we stop here because we run out of time. But eventually, you will see that you can construct the whole table. Yeah. So then next time I will show you that even the proof look complicated, but in practice, this table can be computed very easily. Okay. So we stop here and